Hi, I'm Hyogun from Vision Learning Lab, Gyeong University, working with Jinwoo Choi. I'm going to introduce our work, GLAD, Global Local View Alignment and Background Debiasing for Unsupervised Video Domain Adaptation with Large Domain Gap. Gyeong-Moon and I equally contributed, and this work is advised by Jinwoo Choi and Gyeong-Moon Park. Also, this work is funded by NCSoft. Annotating video data is very expensive. We have video data and human resource, and we let them annotate this video. But human resource usually costs a lot of money. Here's our goal. We have a video dataset which are targeting to use, and we let an AI model to learn to answer what action in this video, but we need annotations which are very expensive. We introduced a labeled dataset which is very similar to the target. Now we'll call it as a source. The dataset will look like this, and we'll let the model to train this, and we again ask the model of the action in this video, but it does not work as expected. Domain adaptation can be one of existing solutions. We'll have a target and source and a model. We can let the model relate them by their appearances. Then we train it again. We call this method domain adaptation. Besides, our dataset is made of videos and our target is unlabeled. Let's call it unsupervised video domain adaptation. By the way, the model is going to work like this. The place in the video looks like road, then ride bike, walkway, then walk, and so on. Then it's just a shortcut with background bias. But real-world data is harsh. Recognize the weather, the format, and their view differences. So the model cannot relate them easily. As seen, existing datasets don't have large domain gaps. UCF HMDB can be an example, which consists of two different datasets, UCF dataset and HMDB. And this task asks us to do domain adaptation, but in fact, they look so similar. There are little differences of backgrounds and action durations. At this point, we're going to introduce our more realistic setup, Kinetics BABEL, which consists of Kinetics as source, BABEL as target. Then we ask to do domain adaptation. As we can see, there are two challenges. The first challenge is its significant background gap between two datasets, and the second one is its significant action duration gap. This plot shows video length as distributions of each dataset, by which we can recognize their difference. Now let's see them quantitatively. This plot shows scene distance in x-axis and temporal distance in y-axis, and each means like this. And our Kinetics BABEL is here. It has much further gap, so we can claim that it is realistic setting. Then how can we tackle the background bias and the temporal gap? Our proposition is GLAD. We have a basic structure to predict actions, and GLA model to deal with the temporal gap, and background debiasing models to deal with background bias. Before we go deep into it, I think I should talk about what global and local features are. We'll have a video in frames. But we'll not use all the frames, but we do samplings, uniform and dense. In uniform, we have a long interval, and we can regard it as a global feature. In dense, now a short one, and this is going to be a local. And I'm going to go over another existing idea, a domain classifier. Now we have source and target videos. We'll make them fed into the backbone. The output will be features. And the domain classifier predicts which domain each video came from. And we'll have a gradient reversal layer, which negates the gradient. And now the feature extractor wants to increase the loss. To do so, it should fold the domain classifier. So it generates domain invariant features like this. Later in evaluation, you can use this feature as an input to the action classifier. But with the big temporal gap, now we'll have long and short videos. In this case, the feature extractor generates so different feature in early training, and it is too easy for the domain classifier, which means that it's gonna generate no gradient flow. What if we apply two sampling methods simultaneously? That's for long, uniform for short, like this. And then they can generate similar features. The global-local view aligner consists of three different classifiers: global, local, and global-local. Then we have source and target videos, and global and local features from each. For globals, we compute the loss. For locals, for global-local, we use both features and choose in every step and compute the loss. Now we can have gradient flow. For background bias, we choose two techniques. The first one is background augmentation. We have a video. If we apply temporal medium filter to it, we can easily get its background. So we'll make a background DB. With this DB, we can do background augmentation. When a video comes in, we choose one background in the DB, and we blend them to get this. This simple idea can prevent the model from exploiting the background as a hint. The second technique is temporal ordered learning. This is a model, and we'll have a video. We can sample multiple clips from it, and we shuffle them, fitting them, and let this model predict the order. Then we compute the loss. If the extractor is biased to background, the MLP cannot determine the order, which means it is debiasing. Let me show you the performance of our model. Note that we use I3D in this case. Source only and target only means lower and upper bounds model can achieve existing methods. This is ours. Only with fewer frames and clips, GLAD surpasses DNN as well as the SOTA. Now we show whether we'll show whether GLA and debasing methods are compatible to each other. The backbone is TSM here. The plain model, only with debasing and only with GLA, we can achieve pretty high score. But with both, we can go further. Now we can make GLAD by GLA and debasing. GLA works on longer and shorter actions. This is video doing a pickup. This is very short. Most predictions. Well, DNN went too far as it overestimated the action from just an action picking up. But GLAD works. In a longer one, which is a dance, it looks like DNN focuses only on its local actions, but again, ours work. Conclusions. We addressed the challenging problem of UVDA, focusing on scenarios with large gaps. We introduced the task Kinetics BABEL, which is more challenging, large, realistic. We proposed the method GLAD, which can deal with large background temporal gaps. The opposite direction, BABEL Kinetics, is left as future work. You can find our repo by this QR code. Thank you again for listening.